All right, so I'm starting the streaming to YouTube. So this way, everything is going to be recorded, and I will put the link in Zoom in the chat. So I'm just putting a link in the channel chat. Okay, can you guys see that?
No.
That's the channel chat, not the usual chat. But I can also put it in the usual chat.
Yeah, I see it.
Okay.
Yeah.
Yeah, but I can put it into the usual chat to just so that we can have it both ways. There we go. All right. So since she's just trying to look up her password to sign in, we'll wait a little bit.
So can I ask, are you a full-time professor or do you work another job too?
I do have a part-time consulting job that would not that wouldn't leave. But I do teach full-time at American River College.
Oh, okay.
Yeah, I teach mostly programming classes. The typical class, the two classes that I usually teach every semester, one is assembly language programming, and then the other one is discrete structure, which is basically a math class. And that's not her. The interesting part was when I first started teaching, I was teaching assembly language programming, but using the System 360, IBM's System 360 processor core. So that was kind of interesting because that was 20 years ago when I started to teach the mainframe assembly language, and so now 20 years later, I'm getting back to talk about mainframe concepts. All right. So does anyone know whether Tway is still having issues getting in, or?
Did you send her, you sent her one of those invites like you did us, right?
Yes, because she's
Through
in the
the Zoom
channel.
channel?
Yeah,
I'll
because
tell her
she's in the
try.
channel already.
Try doing-
I can double check and make sure, but I'm fairly sure that she's already a member of this channel. I'm just double checking right now. Yeah, so it shows that she's already a member of this channel. So when I send that invitation to all of you, she got one too. All right. I'm looking at the time. It is 5 minutes past, so I think I'm going to get started. Since everything is going to be recorded, because what you're seeing through the screen share is recorded, and the streaming is on already. I can put that up to just so that if Tway wants to catch up with us, she can also use that to help her catch up. So I'm going to put it in both the usual chat and also into the channel chat. So in this case, the channel chat is actually better because it is persistent. Because otherwise, if whenever Tway signs in, the chat that has already happened, the text chat of the video itself that has already happened up to this point, she cannot see anything. But on the other hand, the channel chat is persistent, so she can actually see everything in the channel chat, and that's why I personally prefer to put things into the channel chat and not so much into the usual chat that people think of when they use Zoom. All right, so I'm going to get started. Assuming that last time we talked about Type 1 Hypervisor. What we are doing today is to continue and talk about operating system. So operating system is usually just abbreviated as OS, in computer science or in ICT in general. An operating system is basically a software component that usually runs directly on
Jack,
top. Yeah,
I don't mean to interrupt.
go
She
ahead.
just texted and said she can't figure out how to join.
Um, Okay. Can you guys send her the video link?
Right click on the message that said what did it say?
I don't see anything new in the chat except thank you, Lupe, for your contributions.
Below that, I have one that says incoming call.
Mm-hmm.
Oh,
And then if you right click on that, if you hover over it, there's a set of ellipses.
There she goes. She's there.
oh, she figured it out. Okay.
Oh, okay. Good job.
There we go.
All right. Okay, I'm just double checking, making sure everybody's here. Yay! Okay, so everybody's here. Excellent. All right, so I'm getting back to well, let's go back to Type 1 hypervisor first. So a Type 1 hypervisor is basically a software component that runs on quote-unquote bare metal. Okay, so the term bare metal simply means there's nothing in between a Type 1 hypervisor, which is a software component, and the actual hardware of whatever computer system we are talking about. So the IBM Type 1 hypervisor, I believe, is ZVM, which I guess stands for Z virtual machine. A Type 1 hypervisor has a kind of interesting job to do, because what it is trying to do is to create the illusion that there are multiple hardware setups. So in reality, we only have one hardware setup, but what a Type 1 hypervisor is trying to do is to create the illusion that there are multiple hardware setups. So in the case of a PC, okay, what you saw last week, I demonstrated that I could run Windows inside Linux. So in that particular situation, I have a Type 2 hypervisor, which has the same kind of job, but it doesn't run on bare metal. But the job of that hypervisor, nonetheless, is to create the illusion, to Windows in this case, and go like, hey, this is a PC. I have a speaker, I have a mic, I have a screen, I have memory, and here we have the processor, and here's the network interface card, and so on. So all of those things are either borrowed from the host operating system, or they are just completely, fabrications using software, using programs. Okay, so when Windows loads, it doesn't, if it needs to know, I suppose there's a way for Windows to know, but I don't think, normally it needs to know. So when Windows boots up inside, on top of a Type 1 super hypervisor, Windows doesn't care. It's like, okay, I got my memory, I got my hard drive, I got my network card that is connected to an actual network. I got my screen, I got my sound card. I'm good to go. So Windows just run normally, doesn't run any differently compared to running on quote unquote bare metal. So that's a good segue to 2.3, which is operating system. So Windows in this particular example is an operating system. It normally runs on top of bare metal, but in the case of having a Type 1 hypervisor, the operating system is running on top of the Type 1 hypervisor. I believe we had a spreadsheet last week that demonstrated the multiple layers. So if you want to pull up that spreadsheet, or if you have jot down notes about that spreadsheet, you would see the Type 1 hypervisor is in between an operating system, which also includes ZOS, and the bare actual hardware, processors and friends. So do we have any questions at this point about these concepts? Okay. So without any questions, there's also I believe this is what we talked about last time too, is the term LPAR, or logical partition. So a logical partition is basically a virtual, basically is a virtual machine, but using IBM's terminology. A virtual machine does not natively have an operating system. All it really is just a machine with nothing installed. So that's what an LPAR is. So on top of an LPAR, we can install ZOS, and now it becomes an installation of ZOS. All right. So now we can talk about an operating system. Okay, in the sense of what does it do? Okay, what does an operating system do? What is its job? The job of an operating system is to offer services. In other words, it doesn't let other things, we know those as jobs or subsystems. So those entities, those software entities, they do not directly, go to the hardware, or the pretense of hardware in the case of a type 1 hypervisor. So the subsystem and the apps, they do not go straight to the hardware and go like, I'm going to use this chunk of memory as my own. Okay, because if everybody just kind of do this without any coordination, bad things are going to happen, right? Because each subsystem or each job doesn't know what the other ones are using. They can step on top of each other. Resources may not be utilized efficiently, and so on and so forth. So the job of the operating system is a supervisor. Okay, it is here to supervise and coordinate. What is it supervising? It's supervising the subsystems, it's supervising the applications, it's supervising the jobs. What is it coordinating? It's coordinating the allocation and the deallocation of resources. That's the job of the operating system. That is also why the name of that's why the software that supervises the operating system is called a hypervisor, because hyper is more super than super. So the supervisor of a supervisor is the hypervisor. So that's why we call the software that pretends to have more hardware the hypervisor, because the supervisor, the operating system, runs on top of that. So do we have any questions at this point? Because these are kind of abstract concepts. There are very few real life examples that I can give to explain these things.
So the hypervisor actually supervises the operating system?
Right. So the hypervisor creates the illusion of additional hardware so that the operating system doesn't even know, and it would just go like, hey, I need 4 gigs of RAM, I need a hard drive, I need a network card, and so on. So that's what the operating system wants to access as its resources. But in the case where we have a hypervisor, a type 1 hypervisor, the operating system actually does not get to the hardware. It doesn't get to what we can see physically, because the type 1 hypervisor is in between, and the type 1 hypervisor now has a chance to say, okay, I see that you want to use 4 gigs of RAM, but I'm going to give you 2 gigs to begin with. As when you use more, I will allocate some more from the actual physical RAM. So the hypervisor is in between the operating system and the actual hardware. So when the operating system thinks it is actually directly, accessing hardware, it's not.
Okay.
All right.
Mm-hmm.
Okay, very good. So depending on the application, an operating system does not need to be aware that it is running on top of an LPAR or logical partition and not actual bare metal hardware. Most operating systems are designed and written to run directly on bare metal hardware, but they also can run on top of a hypervisor, because if a hypervisor is doing its job correctly, it should be completely transparent. So the operating system does not even know that it is running on top of a virtual machine instead of the actual machine. The last paragraph here says an operating system can potentially interact with a type 1 hypervisor to manage resources dynamically, but that usually does not happen, because that sort of defeats the whole purpose of having a type 1 hypervisor. In the case of load management, I can see how the hypervisor can be also utilized to manage resources. It's like, okay, we have 8 virtual machines on one single physical installation. So if one is overloaded and the other 7 are just kind of slacking off and not having enough work to do, we can sort of go like, okay, maybe we can just, kind of reduce the amount of processing resources allocated to a particular L part, the one that's, the 7 ones that are slacking, and then we can allocate more resources to the one that is overloading. So the hypervisor also creates, a point where we can, perform load management. Load management is also associated with load balancing. So load management is more specific, and then load balancing, I should say it the other way around. Load balancing is one of the things related to load management, but load balancing is a very important concept when we have things that can quote unquote spread out to multiple installations. So when we get to the load management module, we'll talk about those concepts more. And now we move on to subsystems. So a subsystem is an IBM term. Other operating systems like Mac OS or Linux or Windows, they do not make use of the term subsystem. They basically call those things as daemon, D-A-E-M-O-N. I'm not sure whether I pronounce it correctly or not. Or they call those things as quote unquote software servers. Okay, to distinguish them from hardware servers. So these are the more common term outside of IBM. So when you hear these terms in a Linux or Unix environment, or when you hear about this term or a service, okay, in the case of Windows, they are about the same concepts as a subsystem in the case of IBM terminology. So what exactly is a subsystem? A subsystem is, first of all, it is a software component. So there's nothing, there's no hardware to a subsystem. It is a completely software entity. And what it relies on? It relies on the operating system to provide certain types of services and resources. So what kind of resources are we talking about? Okay, it requires RAM, it requires memory, it requires access to the mass store device. In the case of IBM, is your DAS-D. It might require access to the networking card, okay, because it can say, I'm listening to this particular IP address at this particular port, so that people can ask me about things, okay, in the case of DB2 especially. So those are the things that a subsystem is relying on the operating system to provide. And that is why we have an operating system before we can install subsystems, because the operating system provides the basic services that a subsystem requires. So now the next question is, once the subsystem has all the resources that it requires, what does it do? Well, a subsystem in return offers its own resources and services to either other subsystems in some cases, but most of the time it offers its resources and services to applications and jobs. All right, so we can think of an example here. Okay, so DB2 is a very important subsystem in IBM mainframe computers, because it's a database server and many applications are now database driven. So in that case, DB2 is relying on ZOS, because ZOS is the entity that will say, okay, so DB2, you need 8 gigs of RAM to store your tables and your cache and whatnot. Okay, so ZOS would be the one allocating the memory, so that DB2 has that much memory to play with. DB2 can also ask ZOS and go like, okay, I want to listen to this network port, okay, which is specified by an IP address plus a port number usually. And ZOS has to deal with the actual network card. It has to understand TCP/IP and so on and so forth. But by the time ZOS says, okay, here is the port, go ahead and listen to it, that is the interface between an operating system and a subsystem. So what DB2 does is it will listen to a network port, and without anything else going on, a subsystem doesn't do anything actively. Normally, it doesn't do anything actively. It might take a little bit of processing resources just to quote unquote keep alive, okay? Just to check and make sure everything else is operating normally, but it won't take up a lot of resources normally. What it does is to wait for clients to connect to it, or it waits for clients to make use of its services and resources. So when we talk about clients in this case, those will be known as applications and also jobs in our context. So are we okay with those terms? What is a client, what is a server, and so on?
Yes.
Okay, excellent. So now on top of a subsystem, so now that we have ZOS and on top of ZOS we have DB2, now we can start to have applications or jobs that make use of the database. And up to this point, okay, everything up to section 2.4, these are all IBM products, okay? They are complicated, systems. They are very expensive, but up to this point, they don't do a single thing that is useful by itself to the DMV, to the Board of Equalization, to the Franchise Tax Board, and so on. Because up to this point, they are only providing an infrastructure so that we can have applications and jobs to run. So only at this level, at section 2.5, that we are doing something that is specific to an enterprise, to a government agency, or to a corporation. So a job, which is kind of the same as an app or application in the context of other operating systems, specify work to be done that serves a client-dependent purpose or value. So when I use this word client in this case, I'm referring to the actual client. I'm referring to the DMV. I'm referring to the Franchise Tax Board. I'm referring to the Board of Equalization. So that's the client we are talking about. It's an organization. So for instance, a certain job may print all the social security checks for a particular month for a particular region in the country. That job is in this particular layer. It is a job, it is an application. Another job may update a database and determine the registration of which vehicle or which vehicles are almost due for renewal. So these are the jobs that the programmers or developers, of a particular agency are going to develop. And this layer is what generates or originates most of the work in workload management. In other words, without applications, without jobs, the mainframe computer is nothing more than a gigantic, super expensive heater because it doesn't do anything useful. It is because we have applications, we have jobs, that a mainframe computer will start to serve a particular organization. So are we okay with the entire section 2? If we have any topics that we want to discuss, now is a good time. Okay, I'm also looking at the text channels, to make sure that I'm not missing anything in those channels. Okay, looks like we are good to go. Move on to the next section. All right, so we'll move on to the next section. So within the IBM documentation, they would refer to the concept of an address space a lot. Okay, so this is an important concept in understanding how mainframe computers operate. Now, the term address space is very general in computer science. In the context of virtualization, an address space has very specific meanings and has very specific importance. So when we have a program in execution, when I refer to a program in execution, that program can refer to a job, it can refer to an application, it can even refer to a subsystem, and even the operating system itself. Okay, so all of those are software components, and every single component in execution is called a process. with only one exception to this rule. The only exception to this rule is a type 1 hypervisor. A type 1 hypervisor, even though it is a software component, but when it is running, it is not usually called a process. So a process cannot exist unless you have an operating system, because it is a higher level concept that can only exist once you have an operating system or something that can understand, what is quote unquote dispatchable. Okay, we'll talk about dispatchable in the next module when we start to talk about workload management. So if you think about the program, being stored on a drive, you can think of that as an operations manual or an instruction binder that is stored in the library. Okay? And a process is a worker that is actually doing work based on the instruction. So this analogy is very loose, okay? It's not exactly, correct or accurate, but at this time, you can kind of think of it that way. So when you have a job that is stored on punch cards, or when you have a job that is stored on a magnetic tape, or when you have a job that is stored on a DASD, that is nothing more than just a binder that is stored somewhere within a warehouse. It is not being utilized, okay? It is just there. But when you have a person following the instruction binder or the operations manual, that becomes a process. So a process is an instance of a program working. So a process is the state of work being done according to an instruction binder. So that's kind of using the analogy of a worker and an actual instruction binder. And I use, the proverbial shoe. So when people say, okay, step into my shoes and see how you like it, that's kind of what a process is. And the funny part about this is the actual processor, which is the person, in the shoes, that person can step into the shoes of someone and then walk a few steps and then take off the shoes and switch to somebody else's shoes and walk a few steps, step out of those shoes, and so on. So this is multiprocessing, okay, which is also a concept that we need to talk about. This is how a single processor. Now, modern computers have multiple processors, and each processor has multiple cores and so on and so forth. But if we simplify the picture and basically say, okay, let's go all the way to the simplest possible processor that has only one core that can only do one thing at a time, it can still give us the pretense that it is multiprocessing, meaning that it is actually doing multiple things, quote unquote, at the same time. And that's because every process, kind of keeps track of where it is, and it is possible for a processor to go into a process and go like, okay, we can do this process, we can perform the instructions of a process for maybe 2.5 milliseconds. When the time is up, the processor goes like, okay, I'm going to have to pause this particular process. Let me move on to the next process that is also just partially done, execute instructions in the other process for 2.5 milliseconds, and then stop or pause and then move on to the next one. So this mechanism is called round robin. It is called a scheduling mechanism, which is basically just saying how do we determine which process gets the processor's attention next. That is the way that we create the pretense of multi-processing, okay, that a computer can work on quote unquote multiple things at the same time. So a process is more or less really just a state, okay? Anyone can step into the shoes, basically the process, walk a few steps, and then take off the shoes. Seconds, minutes, hours, or days later, okay, another person can come by, step into the same shoes, walk a few more steps, and then get out of the shoes. So we are basically looking at, it's really hard to find a real life analogy to describe this, because we normally cannot do something like this, okay? It just doesn't happen with people. But basically what a process is really just how should I put it? I'm just trying to think of, an analogy that you guys can just kind of visualize and go like, oh, so that is what the process is. So think about, okay, this is the way to do it. Think about 10 pairs of hiking boots. Okay, so now we have 10 pairs of hiking boots. And we have a national park and and then we have different routes, different trails. Okay, so what we can do is to say there's only one person. Okay, so we'll pretend that there's only one single person in this entire story. So this person will put on hiking boots pair number 1, go on to trail A, and walk a few steps. And after walking on that trail for 5 minutes, this person can say, I'm done at this point with this trail. I want to switch to another trail. So what happens in that case is this person, just by magic, okay, just magically will teleport from this pair of hiking shoes to the next pair of hiking shoes. But the hiking shoes stay in place. So now we have hiking shoe pair 1 of hiking shoes somewhere in trail A. Okay, but the person is teleported to pair 2 of hiking boots. So now that person will just go like, okay, I'm gonna follow trail B with hiking boot pair 2. Do it for 5 minutes. Okay, so this person will now be somewhere on trail B, but 5 minutes is up, right? So now this person will teleport back to hiking boot number 3, and then use that pair of boots to hike on trail C for another 5 minutes. So you can kind of imagine that you have 10 pairs of these hiking boots. Each one is on a particular trail, okay, making its own progress through the trail. But there's only one person. This person gets to teleport between the hiking boots. The hiking boots stay on the trail, but the person does not. So the person gets to teleport from one pair of hiking shoes to another pair, walk a few steps, then teleport to yet another pair of hiking shoes, and then walk a few steps. That is kind of what is going on with multiprocessing. So the boots are the processes. The person is the processor. Okay, so the processor, the hardware that can execute instructions in a computer, is the person in this story. The process, which is nothing more than just states stored in memory, would be the hiking boots. And then the trails are corresponding to processes. They're corresponding to programs in execution. So a program in execution can be a subsystem. So DB2 has its own hiking trail. Each job has its own hiking trail. Other subsystems like JES, okay, has its own hiking trail. So I'm not sure how this analogy is going. Is it making things more confusing?
Where's the address space come
Yeah.
in?
That's what I.
What is
gonna
the
ask.
address space? Okay, so address space gets a little bit more confusing in this story. So a address space, let me see how I can put this. It gets a little bit complicated because you can have multiple processes or multiple fronts of execution within the same address space. So it's harder to explain the concept of an address space when we need to account for multiple people walking in the same space. So we can sort of, okay, at this point, we can look at the address space the same as the hiking boots. No. It is kind of a combination between the hiking boot and the trail. So when you look at those two, at the same time, you can call that the address space. I'm still thinking about the analogy. Okay, scratch that, scratch that. The address space is the hiking trail. All right?
That's where I was thinking.
Yeah, the address space is the hiking trail. So in a very confusing way, you can actually have multiple boots on the same hiking trail. So we'll explain that later. But if you want to know what that term is, those are each one is called a task. Okay, so a boot is really a task, a TCB, a task control block. But we'll get to that. Okay, don't worry. We will get to what the task control block is, because we need that concept to explain certain other concepts in workload management. Is that okay?
Yep.
All right. So on the side, if you guys are taking notes, you can start to draw like, boots, hiking trails, and then assign, IBM terminology to those things. I'm not sure how you're going to draw the person who can teleport from one pair of boots to another pair of boots. All right, so that is the concept of address space, and there are 2 or 3 main types of address spaces. The first one is the physical address space. The physical address space is determined entirely by what you can see in a mainframe computer. So the actual RAM, random access memory installed in a CPC, which is central, okay, it's typo here, central processing complex, or just, if you want to look at it as just the computer, that's perfectly okay. Okay, so, so if you don't want to refer to a mainframe computer as a CPC, you can just call it a computer or a PC, okay, a personal computer. So with a normal personal computer, we have sticks of RAM. Those are called DIMMs, DIMMs, and it is an abbreviation of dual inline memory module. Okay, and they're physical. Okay, these things you can buy from Amazon. They comes in a package, and when you unbox it, you will see a circuit board with some chips on both sides, and then it has a lot of little contact points, and you push it into a slot inside the computer. It is physical. Okay. So the actual RAM installed in a computer has a address space, and locations in an address space are sequentially numbered, and that's pretty much the physical address space. So one way to kind of visualize the physical address space, or any address space, is really just like a binder with a lot of pages, and then every single page has a page number. The page numbers are they are sequentially and contiguously numbered. What that means is we have page 0, page 1, page 2, page 3, page 4, and so on, and the numbers go all the way to the very last page. So every page, which corresponding to a location in memory, has its own address. So collectively, from page 0 all the way to the very last page number is called the address space. That refers to the entire binder with all of these pages corresponding to locations in RAM. So are we good with the first paragraph at this point?
Yes.
Okay, very good. So now we move on to the second paragraph. A Type 1 hypervisor allocates one or more regions of physical space to each LPAR. So an LPAR is kind of like you can look at those as virtual binders, and basically you're creating these virtual binders to hand out to the operating system. So that each virtual binder has a mapping to actual physical RAM, but sometimes it is virtual, which means you can trick the operating system and say, okay, I'll give you a concrete example. Let's just say that the computer actually only has 8 gigs of RAM. I know 8 gigs is not a lot, but the amount is not the issue here. Okay, so let's just say that physically you only have 8 gigs of RAM, and you're creating 4 LPARs, logical partitions, and then each logical partition says, I need 4 gigs of RAM. So now you think, oh, that's not possible. Okay, because I only got 8 gigs of actual RAM. I can see how we can allocate 2 gigs of RAM to each LPAR and there are 4 LPARs. That seems okay, that seems doable. But how can we allocate 4 gigs of RAM to each logical partition? Well, that's because you can promise more than what you can deliver. Because you can have virtual memory. Okay, so memory allocated to the LPAR can be actual. It actually maps to physical address space, but it can also be virtual. You're basically just telling each LPAR and go like, yeah, you can go from location 0 to 4 billion something. They're all here. But in reality, they are not actually in physical RAM. Okay, so how this can be managed, we'll explain that after the workload management thing, because this has to do with virtual memory, it has to do with swapping and a lot of other concepts in the operation of a modern computer. It's not just mainframe. By the way, these concepts also exist in regular computers. But the idea that we want to get across in this particular context is there's only one physical location 0 in physical RAM. There's only one of them, okay? But using virtualization, using technology, using software, we can have each LPAR having its own location 0. So location 0 of LPAR 1, LPAR 0 may go to a certain location in physical RAM, and then location 0 of LPAR 1 can get to another location in physical RAM. So what the type 1 hypervisor can do is quote unquote remapping the address spaces. Are we doing okay so far with this analogy, or is that kind of a little too much?
Why is nobody else talking except for me?
We're thinking.
I'm
Okay,
good so far.
keep thinking. That's okay. You know, I like
Mm.
you guys to be thinking while I'm explaining these concepts.
I'm still struggling with the address space itself.
Okay.
I
An address space is, you can look at it as just a bunch of memory locations. It's just a binder. Okay, that's all it is. It is just a binder. It has a beginning, it has an end, it has a whole bunch of pages, you know, sequentially numbered in between. That's it.
okay. Yeah, I'm just confused about stuff that we haven't got to yet. So
Okay.
okay.
Yeah. So when we get to those, you know, we can try to explain those things. So physical address space is just referring to RAM that you have installed in a computer. And this particular address space only has one single location 0. But when we allocate memory to the LPARs, each LPAR can have its own location 0 because of the hypervisor. Because the hypervisor is sitting in between the actual physical hardware and also the LPARs. So when LPAR 0 says, hey, I need to get to my location 0, the hypervisor is sitting in between and go like, okay, your location 0 is actually, you know, physical location 20, because the hypervisor maintains a map. Okay, so it knows if this LPAR is looking for location 0, it is over here in physical space. If LPAR 1 is looking for its location 0, it is over there, and so on. And the hypervisor, a type 1 hypervisor, is doing this job in between the LPARs and the physical resources. Is
So
that
it
okay?
might not be the actual location is not actually 0 because the hypervisor is the one who's maintaining the actual location, but the LPAR thinks it's got location 0.
Exactly. Exactly. So when the LPAR talks to the hypervisor, because remember, the LPAR doesn't know it's talking to a hypervisor. The LPAR thinks it is talking directly to the hardware. but what it thinks is directly talking to the hardware is actually the hypervisor. It's a type 1 hypervisor. So when the LPAR says, okay, I need to get to location blah blah, okay, then the hypervisor will first look up, okay, who are you? Which LPAR are we talking about? Oh, I'm LPAR 2, okay? Then the hypervisor will look up a table. It's a complicated table, but we'll just say it is a table. It will look up a table and go like, okay, you're LPAR number 2, and which location do you want to get to? So the LPAR can only say what location from its perspective. So the LPAR would say, I want to get to location 5 as far as I'm concerned. The hypervisor would take both pieces of information, which LPAR we're talking about, and what location this particular LPAR want to access. It would use the table and look up the actual physical RAM and go like, okay, that is actually over here in physical RAM, because it has a lookup table to translate which LPARs, which location is where in physical RAM. Are we good
Got
so
it.
far? Go ahead.
I am.
Okay.
I have a question.
Yeah, go ahead.
Can you just explain, like, in simple terms, what is an LPAR? Sorry. I know it's logical partition, but
It doesn't tell much, right? It doesn't say much. What is a logical partition? It is also known as a virtual machine.
okay.
It is a pretense of a machine that is not actual. So the hypervisor is creating this illusion. So a hypervisor has access to the actual machine, but using the resources of the actual machine, which in this case is a mainframe computer, the hypervisor is creating an illusion of, okay, we actually have 6, different machines here, 6 different LPARs.
So LPAR is a software, or
An LPAR is an illusion created by software, and that piece of software is known as the Type 1 hypervisor in our context.
okay.
I'm not sure how many of you watch ninja-related, kind of anime or movies. And, a lot of times, they say these ninjas can create clones of themselves, right? So, so this is a trick, where they can approach an enemy instead of having one single ninja, which is easy to stop. Now you have like 16 of the same ninja running around, and you don't know which one is the real one, right?
Right.
That is kind of, so the clones are kind of what an LPAR is. They are
Okay.
not actual, they're not physical, but in the context of computing, the LPARs can do actual real work, unlike in the case of a ninja clone, which is just an illusion.
Okay.
I think I can help Jennifer relate to what she do.
Okay, go ahead.
Jennifer, from what I understand, LPAR could be your test system, your production system, your development system. Like for me, the test is like sandbox. For CDT is Site 9, HWDR, COA 9. For development, production is S1. That's all I remember from my side. Hope that helped.
All right. Well, thank you, Tway.
Okay.
So,
Would it be fair to say an LPAR is an instance of an operating system where you have one physical system, but it can be divided into multiple different operating systems. So you could run, in like a PC type environment, you could run Windows on one system, you could run DOS on another system, you could run Linux on a third system. They all physically exist on the same system, but they run independent of each other.
sort of. So I just want to be picky about, the terms that we use, not because I really want to be picky, but I want to make sure that the terms are understood separately. So let me see if I can do this. I'm not sure because I have never tried it. So I'm just going to run QEMU, which is a type 2 hypervisor on its own without anything installed. Okay, so I want to run this on its own, and let me see. Okay. All right, so I just ran QEMU by itself, and this is the screen that I get. This is an LPAR. Okay, it is just a machine with a BIOS, with a virtualized hard drive of some kind, a virtual network card of some kind, and a virtualized sound card of some kind. But you can see that it says, hey, nothing, I cannot boot this. Okay, this is what happens when you have a real computer, but you haven't installed anything on that computer. That is what an LPAR is equivalent to. Are we good so far? It has no operating system. An operating system is installed on top of an LPAR. An LPAR is providing the resources so that you can install and run an operating system. All right, so I want to keep this screen here, and I'm going to run another command. So with this one, I want to go to my Windows 7 folder and run this one. And I want to move my window over here. Now, this is an LPAR, but this is an LPAR that actually has Windows installed on it. So let me show you side by side the two virtual machines. So on the left hand side, the one that says LWT, this is an LPAR, but it has Windows already installed. On the other side over here, we have an LPAR, but has absolutely nothing installed. Is that okay? I want to help you guys differentiate what an LPAR is and what an operating system is. An operating system runs on top of an LPAR. An LPAR by itself is fairly useless because it has nothing installed. It just says, hey, I'm a box. Okay, I'm a PC, I'm a box, I have a hard drive, I have RAM, I have network card, but I don't know how to do anything because there's no operating system installed on the virtual hard drive. Once you install an operating system in an LPAR, then you can run the operating system itself. Is that okay? Is that helping to differentiate?
So the LPAR is the virtual hard drive?
The virtual hardware, not just the
Hardware?
drive. Everything is virtual. The hard drive, RAM, the display, everything is virtual. Because from the perspective of, okay, let me get back to the LPAR that has nothing installed. So from the perspective of this particular LPAR, it has its own network card, it has RAM, it has a hard drive, it has a hard drive controller, it has everything that is needed to run an operating system, but an operating system has not been installed yet onto the hard drive, and that's why it says, hey, I cannot boot to any operating system. The other one, which is the one over here, is also an LPAR or virtual machine, but on this particular virtual machine I have installed Windows 10. So an operating system is running on top of an LPAR. Without the operating system, an LPAR is fairly useless by itself. Is that okay?
Right. Yeah, I got it.
Okay, excellent.
Up to this point, maybe I
No,
have
that's
a few
good.
more questions later.
Yeah, absolutely. Anytime you guys have any questions, just go ahead and pause me and just ask the questions, because the worst thing that can happen is not asking the questions and just keep going. That's going to do more harm than good. All right, so I'm going to close this one off, and I have to be careful not to just kind of close the LPAR. Okay, so this is the other thing about LPARs, but I don't think you guys have to worry about this, is even though okay, you don't have to worry about this at all, okay? I will explain why. because QEMU is a type 2 LPAR, which means, to Linux, which is the operating system that I'm using right now, QEMU is nothing more than just a program. Okay, it's just kind of like a browser or a word processor. It's just a program. So I can just, close the application itself to make it go away. But if I do this, okay, if I click this close button, it is the same thing as pulling the plug on a computer. Can someone explain to me why, if you can do something, if you can help it, why don't you want to pull the plug of a computer to turn it off?
Fragmentation on your hard drive. Resources are, I guess, still allocated, but they never get released.
They never get committed. Okay, so you can have an operation that is in progress, okay, while you unplug the computer. So your hard drive controller may be writing a sector, in the process of writing a sector onto the hard drive, but at the very moment that you pull the plug, or at the moment that the hard drive controller loses power, that sector may be halfway written. And that's kind of one of the worst things that can happen, because when the sector is halfway written, the older half is overwritten, but the newer half is also partially written onto the same sector. And unless you have a file system that has resistance to this sort of thing happening, you can lose data. Okay, you can lose a lot of important data by doing stuff like that. And that's why it is never ever a good idea to unplug a computer. Just say, okay, I'm just going to pull the plug to shut down the computer. Sometimes you don't have a choice, okay? And especially with laptop computers, sometimes you don't have a choice. But if you can help it, don't do that, okay? So if you can help it, you want to kind of shut down the system in a quote-unquote soft way. And in the case of an LPAR, the Type 1 hypervisor usually would offer you a softer way to turn off the computer. So in this case, I can go to Machine and I can click this Power Down, which is kind of still bad, okay, but it's not nearly as bad as just clicking the Close button over here. Okay, so I'm gonna click Continue so that this virtual computer has a chance to finish the operation, and I can kind of pull this to the side because it is not important anymore. All right. So yeah, go ahead.
At CDT, one of my mentors was training me, and she said that when we go out of one of the LPARs, that it's always best to go back to the ISPF panel, the menu panel,
Mm-hmm.
and then close out.
Make your
from
computer
there
easier
for that
to
same
use.
reason, so that things aren't trying to process in the background, and then you shut out and you could potentially harm something.
Right.
So, and the ISPF would be a software product, right? That
Yes.
is put on. Yeah. So that's the same kind of thing. And then close out and log off from there.
Yep.
Okay.
Exactly. The ISPF is in the absence of graphics cards, and only with dumb terminals, that we know as the 3270, terminal. With only that kind of technology available, the ISPF was the best IBM could do to make a user-friendly interface. But it is still an interface to the operating system. It is still a way for a person to interact with the operating system. So you can initiate a shutdown, you can start a subsystem, you can shut down a subsystem, and so on. So when you ask the system to shut down through ISPF, you are basically gently telling the operating system and say, please do whatever you can to safely shut down the system. So what the operating system would do in that case is to go through every single address spaces, which we'll continue to explain, and say, hey, I need to shut this down. I need to shut down the computer right now. So you might want to finish what you were doing and then you shut down yourself. Okay, I'm not gonna pull your plug either. I want so you're basically telling DP to and go like, okay, we're gonna shut down the system. So you might want to finish up whatever transaction you're processing right now. Finish updating that table that you're currently updating, and then shut down. Okay, don't try to answer to more requests coming in anymore. Okay. And it will do the same thing to JES. It's going to do the same thing to all of the other subsystems. So this way you have a quote-unquote clean shutdown because nothing is partially written or partially updated when the computer is off. So that's a very good um, example of why you want to shut down a computer through the software interface and not just by unplugging it. So that's very good. And I'm just looking at my virtual machine. I'll deal with the virtual machine later. And I want to see if I can just pause it. Yep, I can indeed pause it. All right, that's good. And we can come back here and focus on this one. All right, so we have just talked about the physical address space. So in the case of using a type 1 hypervisor, the operating system is running on top of an LPAR, on top of a virtual machine. And as a result, the operating system has its own address space, which I call the system address space. So the system address space is already virtualized. Okay, it is not one-to-one mapped to the actual physical space, but that's okay because the type 1 hypervisor is sitting in between to do all the translations. Now this paragraph here is also kind of important. Most modern operating systems, including Windows, Mac OS X, Linux, Unix, and also z/OS, implement their own virtual memory as an old operating system, allocate memory to other components like the subsystems, servers, daemons, and applications and jobs. So there are two levels of virtualization when it comes to address space. The first one is coming from the type 1 hypervisor. The second one is coming from the operating system itself. So the address space that the type 1 hypervisor allocates to the operating system, that in return can get further virtualized before the memory space get to subsystems and apps. Same kind of concept, except now you have one additional level of virtualization. Are we still doing okay?
Yes.
Yes.
All right, very good. So now we want to understand why do we have virtualization? Okay, because we talked about virtualization, all of these kind of abstract concepts and kind of complicated mechanisms. Why do we do that, right? I mean, because unless there's a reason why we wouldn't be doing any of this. And IBM has been doing this since the 60s, okay, which I have to give credit to IBM for, inventing technologies, way ahead of the curve, okay. They really originate most of the concepts that we find in modern processors as well as modern operating systems. The first reason why we're doing virtualization is to save money, okay, and I think it was Tway, use an example. So instead of having to purchase 3 actual hardware servers, one is for production, one is for testing, and the third one is for crash and burn. Okay, so it's kind of a testing, except it's even less ready for production. Okay, so now we have 3 different servers because you don't want to normally you don't want to run your test software on the production server just in case something happens. We don't want to bring down the actual services being offered, right? So normally you want to have 3 separate boxes where one box is only responsible for production stuff, one box is only responsible for test stuff, and one box is only used for crash and burn stuff. Well, But that's 3 boxes that you have to buy. Virtualization basically says, okay, just buy 1 box. Okay, now granted, this 1 box that you buy instead of 3 is going to need a little bit more juice. Okay, it's going to have more processing power, more RAM, and also, you're going to need a bigger hard drive space, so that you can fit everything in. But it will still be less expensive than buying 3 boxes. Okay, just the hardware itself. The maintenance is the other part. Okay, where are you going to put the 3 boxes? I mean, we are not even talking about small boxes here. The mainframe computers are still they're still kind of big. Okay, they are not like small. So by combining 3 boxes into one, you're saving not only just the cost of the computer, but also the cost associated with operating the box. Okay, and we can do this. Okay, type 1 hypervisors are fairly reliable, especially if it's coming from IBM. If the the Z virtual machine ZVM is reliable. So now you can actually run 3 virtual machines on the same hardware and not to have to worry about, but what if the test server crashes? Is that going to do anything to the production server? The answer is no, okay, because the hypervisor is doing its job and basically just say, okay, test server, you can crash all you want, okay, but I will make sure that nothing happens to the production server. The production server asks for 50% of all the processing resources. It will continue to get 50% of the processing resources, regardless of what the other 2 virtual boxes are doing. So now you can combine 3 boxes into one, and that's why we are saving money. The second one is also very interesting, and I think it applies to a lot of government agencies as well. It is the insulation from hardware changes. So if you compare, if you think about the COBOL programs that are still running, that are running today, with these servers, you have to kind of ask, when were these programs written, and what version of the COBOL compiler are you using? Are you using the latest and greatest COBOL compiler because the programs make use of the latest and greatest COBOL features? Or are we talking about programs that were written maybe in the 70s, perhaps 80s, and it is still running on using the compiler of the same era? Okay, I don't know the answer to that, but I have a strong suspicion because I have worked with people from the DMV and also the Franchise Tax Board. And they basically say, these are developers, by the way, and they basically said, they're still running tools, that originated from the 80s. Okay, that means it's possible that they may be running an older version of the operating system as well, instead of the latest and greatest ZOS that IBM says, hey, reinstall this one. This is the greatest, the latest and greatest. But the problem is, the older operating system doesn't understand anything about the latest and greatest hardware that the new IBM boxes include. So now you have a disconnect, right? Because you have the older operating system that you don't want to touch, because anytime you upgrade an operating system, you are opening a huge can of worm. Okay? So you don't want to update or upgrade the operating system if it is still working. At the same time, now you have the latest and greatest hardware, this shiny new box, with all the super duper, hardware from IBM is the greatest, thing you can get. But these two cannot talk to each other natively. The old operating system will try to talk to the new hardware and go like, I don't recognize you, okay? I don't recognize this network card. I don't recognize this, DAS-D controller. I don't recognize RAM either, okay? Because remember, the old operating system, they don't even know, they don't understand the address space, beyond a certain point, because that's before we can have, like gigabytes of memory installed even on the mainframe computer. The new computers come with so much RAM that the old operating system just says, I cannot deal with this. Okay, period. I cannot deal with this. So what do? We use virtualization. So the type 1 hypervisor now comes in between the latest and greatest box from IBM and the fairly old operating system that we don't want to upgrade from because everything is still working. So now the hypervisor is sitting in between to basically say, I know how to translate. Okay? All right, old version of ZOS, what type of network card do you want to use? Oh, I can only recognize this really kind of old, archaic network card. Not a problem, okay? So what you want to do with this old network card, I will translate that so that the new network card can understand what you want to do. So the type 1 hypervisor is sitting in between because it understands how to pretend a new piece of hardware so that it operates just like the old hardware. And this gives you the ability to isolate an old installation from hardware changes. In other words, as long as the hypervisor is updated correctly, you can run a very, very old operating system on the latest and greatest hardware. Is that okay? I mean, does everybody kind of understand what I'm saying here?
Yes.
All right.
I was just wondering how much is this type 1 hypervisor? It does everything. It's like a Superman.
It's like a
Right.
super magician. It's not Superman. It's like a super magician because it is creating the virtualization, that the old installation, the old operating system, and the old subsystems, go like, oh, I'm just using something that I'm familiar with, but in reality, it's actually using the latest and greatest super duper hardware that IBM has to offer today. I do not know, how much ZVM is, or whether it is actually part of the deal. The one thing about IBM is you don't ask about how much this is going to cost in terms of software components. Now, you guys can correct me because I don't use IBM, products or services. But I think IBM is more of a service provider than a component provider. They don't sell you the things, right? They don't sell you the things. They sell you what do you want me to do for you. So I think it's a contract thing, okay? If you subcontract with IBM, they would just install whatever is needed. They will give you the components that you need. They will give you the training. They will give you all the education, all the manuals and whatnot. And it is because you're paying for a service. You're not paying for the
Right.
actual
But I was just wondering
things.
because it looks like it fixes everything.
Well, it is very flexible. It's
Right.
not super duper complex. Okay, if you have to think about the complexity of the various software components, I would say the operating system is more complex compared to the hypervisor. So ZOS itself is actually a more complex piece of software compared to the hypervisor. And DB2 is also very complex as well. So I would say DB2 can easily be as complex as ZOS itself. So VM, the virtualization part is not super duper complex, but it does serve a very, very important role because it offers all of these things that we can do once we have virtualization. But very good question. So are we good here? All right. So I do have to say there's one point here. The last sentence is also true because once we have the ability to run ancient operating systems on the latest and greatest hardware that is super fast, nobody wants to upgrade anymore because upgrading is an exposure to risks. So if you can avoid that risk by virtualization, then there's no incentive for people to upgrade anymore. So it will just be, from the perspective of the installations, they are now further and further and further away from the latest version of whatever ZOS has to offer. So there's also this kind of kind of byproduct when we don't need to worry about new hardware, because the old software can run on new hardware because of the hypervisor. 4.3 is very interesting. It's about availability. The reason why I think this is very interesting is because old mainframe applications, they don't really need to deal with availability not as much as we do now. Because in the days of batch jobs, okay, as long as you can finish the batch jobs and everything is done, you can shut down the computer, okay, so it doesn't consume electricity. You can just let it stay offline until you have something to do again. So you can afford to have some time to turn off the entire mainframe computer, go in with your cleaning crew, clean up the computer, make sure everything is dust free. You have no idea how much damage dust can do to the early hard drives. Okay, so you kind of need to keep everything really clean in the server room. So availability is not an issue, okay? Because after you're done, you just shut down the whole system, move in, do whatever maintenance work you need to do, and then you turn it back on again after hours, okay? You can't do that anymore. Okay, this is not something that we can afford to do anymore. Everybody wants things to run 24/7, 365. One particular client of IBM is Wells Fargo Bank. So if you ask the executives of Wells Fargo Bank and go like, so what do you think if we need to shut down the entire data center every day for about an hour so that we can do all the cleaning and whatever maintenance we need to do? What do you think the Wells Fargo executive is going to say?
No, you can't.
Exactly. You cannot, because the cost of shutting down, this is a planned outage. It's not even unplanned. This is a planned outage. If you shut down the Wells Fargo IT system for an hour, even if it is like 2 a.m. to 3 a.m., it's going to cost Wells Fargo a lot of money. It's going to, some clients will go from Wells Fargo Bank to another bank, which does not stop its service for an hour every single day. I think with state agencies, it might be slightly different, where you can actually schedule downtime, because nobody will be using the system anymore. So I can be wrong, I'm not really sure. Okay, but in general, for many clients of IBM, they can no longer afford to have even scheduled downtime. So we are not even getting into unscheduled downtime because something just crashed. Okay, some piece of hardware just decided to give up and die. Okay. So what do you do when you need to be up 24/7, 365, and your uptime has to be 99.999%? Well, in theory, they cannot be done because no hardware can run forever without maintenance or without crashing or without failure. Everything is going to fail at some point. Then what do? Well, the interesting thing about virtualization is you can move an entire LPAR from one piece of hardware to another piece of hardware. Let me say that one more time. You can move an entire LPAR from one box, okay? Basically just one box. Think of it as a box. From a box that you need to shut down to a box that is running. So this way, the quote-unquote downtime, or the time where you cannot provide service, will be measured in milliseconds. At the most, seconds. Okay, we're talking about single-digit number of seconds here, instead of an hour. Okay, that is the kind of technology that we have now, where the hypervisor can transport an entire LPAR from one box to another box, so that the downtime of that particular LPAR is measured in single digits of seconds. Okay, I'm gonna pause to make sure that you guys understand what I just said, and also to understand the implication of the ability to do this. Any questions? Any comments?
What if you only have one box? How could
You
you?
you always have just one box, but you
Right.
split it into multiple LPARs.
Okay, so you can't really do both at the same time. You cannot, eat the cake and have it. So either you go for cost effectiveness, where you have one box and you pretend to have several boxes, or you can have multiple boxes and one, at least one is running as a backup box, so that if the main box or the box that is currently being used as the main server goes like, okay, we need to surface this one, so we need to move the entire LPAR from the running box to the backup box, and then we can shut down the running box. Then you can do whatever maintenance you want. You can swap out components. Because it's already shut down, you can do just about anything you want to do to that box. But okay, having said that, having said that, since IBM is a Surface-based kind of company, if you know ahead of time, and trust me, these hardware running on these mainframe computers, they are fairly good at monitoring their own health. So a hard drive controller, for instance, can kind of tell, a hard drive is about to go. Now, when I say a hard drive, that also applies to a solid state drive, especially a solid state drive. Okay, when the solid state drive is about to go, to die, okay, not able to store things reliably anymore, the controller kind of knows it. Okay, the drive itself knows it, and it will tell the controller, and then the controller will tell the operating system. It goes like, well, according to how this drive is being used for the past year or so, we can reliably use it for the next week or so, or next month or so. It will give you a time frame. Okay, so you can basically say, okay, we know this particular server may need to be taken offline to be serviced. Okay, so if you know this, like, let's say, 4 weeks ahead of time, okay, you can contact IBM and go like, okay, we have a mission critical server and we know that it needs to be serviced within 4 weeks. I don't know. I have never contacted IBM for stuff like this, but it is possible that IBM would go like, okay, not a problem. Guess what? We're going to loan you a second server to run your apps, your mission critical apps, while we are servicing your main server. When the main server is completely serviced, then we'll move the LPAR from the backup, loaner, server back to the original serviced or upgraded server, and then IBM will basically ship the loaner server back to itself, back to its main headquarters. I'm not saying this is what IBM offers. I'm simply saying it is a possibility. Does that answer the question?
Yeah.
So you may not have it, but if your Surface contract with IBM, includes, and go like, okay, if we ever need to have a backup server installed, while we maintain the original server for something that we cannot do while it's still running, IBM may be able to offer this kind of service. I mean, it's going to be expensive because they're going to have to ship you a spare box, so to speak, and also, the labor to install everything, to make sure that, everything gets transitioned, smoothly. It's going to be costly. Okay, but you might have a super expensive contract with IBM to begin with, so they're going to go like, hey, you pay for this already. Sure, no problem. So I'm only talking about technologically the possibility, but whether IBM actually does that with its clients or not, I do not know. All right, so now we finally move on to section 4.4, which is kind of mentioning why we are talking about virtualization when we're supposed to be talking about workload management. So workload management is the coordination of the access to resources so that we make sure important stuff gets done, okay? And the less important stuff, maybe, maybe not, depending on whether we have the spare resources to get everything done. technically speaking, workload management does not require virtualization. So you can basically apply WLM, workload management, without virtualization. But virtualization does allow some really interesting workload management, because now you can actually move LPARs between physical boxes. So it's very dynamic, because you can basically say, okay, we are running out of resources. Okay, we can barely get all the mission critical tasks done, and there's not a whole lot left to do things that we would like to do, but not really, critical to get done. So with virtualization, you can now basically just say, okay, we're going to buy another 2 boxes. Okay, we'll install 2 more boxes into our server room, and because of virtualization allowing LPARs to move from one box to another box, now without any downtime, you can basically spread out the workload so that you can continue to make sure all the mission critical stuff gets done, but now you have the spare resources to get the other stuff that you would like to get done also done. So that is kind of the importance of virtualization in the context of workload management. It does allow a lot more flexibility when it comes to workload management. Because if you don't have virtualization, then you're sort of stuck. Okay, if you run out of resources, you are out of resources. Okay, you cannot just say, okay, I'm just going to buy 2 more boxes and everything will be good again. Nope. Even if you buy 2 more boxes, you're still stuck, because you cannot spread out the workload easily to the other 2 boxes that you just bought. So are we doing okay so far with module 337?
Yes.
All right.
Can we take a couple minute break real quick?
Yeah, absolutely. How many minutes do you guys want to do?
I just need to run to the restroom.
Oh, okay. 5 minutes?
Yeah, that's fine.
Okay, so we'll take a 5-minute break. So we'll be back at 7:05.
Okay, thank you.
Yeah, absolutely. I'm still online, so for the rest of you, if you have any kind of question that you want to ask or points that you want to make, I'm still here. And I'm just gonna get this done so that I can move on. Okay. Oh, right, I forgot about. Okay, this is one other thing you can do with a virtual machine is you can pause it. I just paused mine, and that's why I wasn't responding. So I just unpaused it, and now I can cancel it and do a proper shutdown. And I do this virtual machine that I have running Windows 10 is because the reason why I have this virtual machine is so that when I can move the virtual machine, which is basically just a gigantic file of the hard drive image and also a few configuration smaller files. So I can move everything from one computer to another computer. So instead of running the virtual machine on my current laptop computer, I can back it up, and when I upgrade to another laptop computer or desktop computer, I can just unzip the file and run the virtual machine again, and I don't have to reinstall a single thing because it is just a virtual machine. So I just want to explain what kind of application virtualization can offer even for home computing.
I have a quick question
Yeah.
on why does installation of a virtual machine
Mhm.
on an existing like PC, it require half the space of what my computer currently have?
When you say half the space, are you talking about RAM? How much memory?
Yeah.
That part depends on the virtual machine. Not every machine you can allocate, depending on what you actually need. Let me show you what I mean by that. I'm just gonna zoom in a little bit because otherwise the font is a little small. So if I look at the file, the shell script, that starts this. So you can allocate the number of cores. In this case, I can say, okay, take 4 of the cores, and it consider a virtual core as 1 core too. So this is 1/2 of the cores. So the virtual machine can use up to 4 virtual cores. I'm not sure whether I specify RAM. Yes, I did. So right here, I specify, use about 3 gigs of RAM. So the Windows box is actually not really having a lot of RAM because I only allocate like 3 gigs out of the 16 of my actual out of my 16 actual physical RAM. But also remember, because this is a Type 2 hypervisor, what that means is the 3 gigs of RAM, may not be coming out of physical RAM at all. So a portion of this may be physical RAM, but the other portion can be virtual RAM or virtual memory that Linux is offering. So, if I'm running on virtual memory, it's going to be really, really slow, but it is a possibility. So I'm not sure what virtual machine or what emulator you're running. This is using QEMU, which is an open source emulator. If you're using another emulator, probably VMware, I suspect that you can configure how much RAM you want to allocate to the virtual machine. Are you using VMware?
Yeah, I use VMware.
Yeah, I think in VMware, it has a very nice GUI interface where you can probably specify how much RAM you want to allocate to the virtual machine. So it might have a recommendation. So if you're running Windows, the VMware may have a recommendation and go like, okay, you need to allocate at least this much. But you might be able to override that and go like, no, I think we don't need as much because I'm not planning to do a whole lot in that virtual machine.
Yeah, I did. It recommend like half of what I had,
Uh-huh.
of the maximum that I had, and then I try half. It's okay, but
Mm-hmm.
then I figure it doesn't use that much, so I try lower,
Mm-hmm.
like uh, let's say 8 gig,
Mm-hmm.
and it start running super slow.
Oh, okay. Well, that was when I ran my virtualized Windows 10 box, it only has 3 gigs of RAM. And
Yeah, I surprised that when I saw you say 3 gigs.
yeah,
It's
it's
so
only using
little.
3 gigs, and this is an older computer too. I bought this computer in 2018, and even at that time, it was not the latest and greatest, processor either. It was close. It was a decent processor, but I wouldn't call it a super powerful processor because it is still a laptop computer. It's still a pretty thin laptop computer. And on these computers, the limiting factor is how fast you can extract heat from the processor. And in order to make the computer look nice and sleek and stuff like that, you can only extract so much heat because the fan, and also the heatsink, they're also very miniature. So yeah, so I don't have any problems running Windows 10, allocating only 3 gigs of RAM to the virtual machine. That can also have something to do with the operating system itself, because Linux, I think, in general, is more efficient when it comes to allocation of resources. So that can be part of the factor too. All right. So are we all back?
I'm here.
Okay. All right.
It's
Thank
Kelly.
you. I just want to be sure that everybody is here before we start. So I'm going to start with the quote-unquote homework. Okay, so this is not a very technical homework, but I do
I
want to. I
I
think some of
wanted
you. Yeah, go ahead.
I wanted to talk to you about this because I looked at it a little bit today,
Yeah. Uh huh.
and this homework is not something that we can do internally within our units.
Oh. Okay.
So it would require us to go to a whole different section of the department in order to get this information.
All
And
right.
I don't know if the employees are going to be willing to do that for
Okay.
us.
I'm gonna change it then.
C-
That's okay.
Yeah, I checked with my manager too to find out who in my unit could assist me with this.
Mm-hmm.
And she said nobody. It would be a completely different unit, and I don't know any of them.
Oh. Okay. Okay. I'm gonna scratch it and replace it with something, but I don't know what I'm gonna replace it with just yet.
I mean, because I work like in database, and I know
I'm
Ah.
Kelly works in storage, and Twee works in product support.
Uh huh.
So
and
we're
Lube's in storage. I'm not sure about Jennifer.
I'm in
Jennifer.
production support. So we have some. Is it system administrator that we're looking at?
Mm-hmm.
I know some because I used to work in the IS Information Systems Division,
Mm-hmm.
HR. So I know some system administrators that I can interview. But if the other my other classmates can't do it,
Yeah. Yeah. I'm gonna read. I'll change it to something else. Because I thought if you guys could talk to someone who is actively doing workload management on the mainframe computer and ask that person, you will learn a lot from that person because it's not theoretical on paper anymore. That person can actually tell you what kind of challenges is that person has to deal with in real life and how those challenges are managed and so on.
Well,
So
I think like in our area, the priority of the workload is based on the service agreement that they have with our department.
right, right,
So I know that much.
okay.
So
Because some of you work for CDT, right?
yeah,
So if you
Three of
work for
us do.
CDT, yeah, so if
Yeah.
you work for CDT, then it has to do with your SLA with whomever your client is. But if you
right.
work for Franchise Tax Board, then there's a whole different story because you'll be the client and you specify the SLA, but it's still based on the SLA, but you don't get to directly manage workload management anymore because it's not yours to manage anymore. Okay, so I am going to. I will do something else, okay? But for the time being, we'll just go ahead and move on with the workload management module. And thanks to Lupe for helping me to edit and spot a lot of the grammatical and typos within the document. Not so much the typo, but because I can see the typos, using Google Doc. Um, but when I miss a word entirely, then it's harder to spot. All right, so we'll get started with this one. I don't think we can finish it, so you probably have to read a good portion of this, and then we'll come back and talk about it more on Wednesday. So we'll see how far we can, how much we can talk about, just in the lecture itself. Okay, so we'll get started with the why. Okay, why do we want to perform workload management? So the first thing I do is to mention Moore's law again. Okay, this is the law that basically sets the density of semiconductor components. The density would double every 18 months, which is really really impressive if you think about it. Okay, so the idea is even though modern day Z systems are much more capable than the 360 computer back in the 60s, they are still expensive. Okay, mainframe computers are still expensive resources. So that's why we want to do as much as possible with existing hardware, which also kind of gets back to cost effectiveness when we talk about virtualization. So it is not unusual that an organization may want to specify more work on a server than the physical hardware or the LPAR can actually handle, with the exception that, hey, these things we have to be able to do, or this has to be the guaranteed response time. But those things over there, if you have spare or excess resources, we can get to that. Okay, but it's not really critical that we can get to that. So that is why we need workload management, because we need to somehow translate what we, people and organizations, understand about prioritization, importance, and stuff like that into a specification that the operating system, ZOS, and also the workload management subsystem can understand. So that is basically what this entire module is about, is how do we specify how we want to manage workload in a system. All right, cool. So the first part has to do with a bunch of terms. So we talk about processors, instructions, and address spaces, or address, oh, that doesn't sound good. Address spaces, there we go. So in this case, a processor refers to basically an individual core in a mainframe computer. You can look at CPC again, as a single computer. For the purpose of this module, a processor executes one instruction at a time. This sentence is not true, okay? But for the purpose of this module, we'll just say that that is true, because it just makes things a whole lot easier to explain when we say we can only execute one instruction at a time. And for the most part, how we can execute multiple instructions at the same time is transparent to the end user. So we can still kind of go like, okay, that's not really that important. And then one more thing that is really important here is, in order for a processor to execute an instruction, that instruction has to be residing at a particular location in an address space. So in this case, this address space usually refers to the address space of an app or the address space of a subsystem. Okay, but nonetheless, it is just an address space. It's a big, huge, gigantic binder where you can find instructions for the processor to execute. So the next paragraph talks about specifically what an address space is. So an address space is an active copy of an operations manual binder, where the master version of the operations manual is always locked up in a document control library. So in this analogy, the document control library is basically your DAS-D, okay, your tape drive, or in the very olden days, the punch cards. So in order for actual work to be done, a worker has to follow instructions on an active copy and not the master copy that is still stored in the document control library. So an address space is a requirement in order for instructions to execute. Okay, go ahead. Questions? Okay, I thought there were questions, but that's okay. So that's basically what the next paragraph is talking about. The master operations manual, the master copy itself, is basically a data set stored in a DAS-D or some kind of network device, but it is just stored somewhere. When you need to run something, when you need to run a job, that has to be loaded. Okay, so the operating system is responsible to make an active copy out of the master version, and the active copy that is ready for the processor to execute from is basically what we know as an address space. So an address space is just a binder of instructions in a form that the processor is ready to execute from. Now, the address space is only specifying work to be done. In other words, it is no more than just a portable, binder in the field of a particular operations manual. The binder is not going to get anything done by itself. Okay, so so now we have just talked about the binder, but not so much who is doing the work or how we assign someone to do the actual work. It also helps to understand that every individual steps of this operations manual in the analogy is known as an instruction for the processor. So do we have any questions about these terms? What a processor is, what is an instruction, and what is an address space, and how they relate to each other?
Not at this time.
All right, thank you. Thank you for the confirmation. So now we move on to what a task is. So an address space is just a collection of instructions, okay, how to do something in the format that the processor can understand. A task, on the other hand, is a specific instance of following the instructions of an address space, okay, and I'm gonna fix this here, of an address space to perform operations. So to visualize this, you can kind of imagine a construction business. The masters of operations manuals are locked up in a document control library of the corporate office. So when we have a job to do at a work site, what we do is we first make an active copy of a specific operations manual, so that we can now take the active copy to the work site. So the active copy is our address space. So the address space is corresponding to a binder that we can put into a briefcase, and we can take it to the field, but nonetheless it is just the instructions of how to do something. It doesn't get work done by itself. At the work site, there might be multiple tasks that can utilize the same operations manual. Or we can also have multiple instances of following the same instructions. So that means we can have some trucks spraying water on the work site, or the task. Okay, I shouldn't use truck. So let's just say that the task that we have on hand is spraying water on the work site. Now we can divide the work area at the work site into 4 portions. Each portion has its own water spraying task. So now we have 4 individual tasks, but each task is still done or performed by following the same active manual. So in the term of computers, we now have 4 different tasks, but we only have one single address space. So how do we do this? Well, each task will need to follow and track its own progress. It will have to track its own amount of water used, where it is on the work site, and all the other information specific to that one task. But all 4 tasks would basically share the same operations manual. So is this analogy understood okay, or does anyone want me to clarify any points of this particular section?
So because it's doing the same job, it's going to share the same address space?
Correct. It's doing the same kind of job. It's performing 4 different tasks, but each task is based on the same operations manual. But I don't want to put people into this picture because it's hard to remember the boots. So now we have 4 pairs of boots, because each boot is representing a task. In this case, there's only one single operations manual. So now, depending on which boot you're wearing,
So all 4 boots are going down the same trail?
Not the same trail anymore. So the trail analogy doesn't work too well in this case, because how should I put it? Okay, you have 4 bookmarks. Okay, you have 4 bookmarks and 4 pairs of boots. There's 1 bookmark and 1 pair of boots corresponding to each task. So when a person, there's only 1 person. Okay, just imagine there's only 1 person on this work site. So when that person goes to boot 1, the pair 1 of boots, that person will now use bookmark 1 to figure out what is the next instruction to follow in the operations manual. All right? So let's just say that that person performs that particular task, water a little bit, walk around a little bit, and 5 minutes is up. Now the person goes like, okay, I need to switch to the next task. So when that person switched to the next task, that person is now teleported to boot number 2, or pair number 2 of the boots. But at the same time, that person will now have to say, okay, I'm gonna leave bookmark 1 where it was. Okay, that was the last thing that I did, and I'm gonna leave bookmark 1 over there. Now I'm gonna flip to the page that has bookmark 2. That's where bookmark 2 is located. So this way the person can resume the task corresponding to task number 2 by by understanding where he or she left off the last time this person was doing task number 2. Is that okay?
Yeah.
Okay, so task is basically the boots that we talked about plus a bookmark, so that you can remember in the operations manual where you can find the next instruction to execute. Are we good?
Yes, thank you.
All right. So you probably would imagine, it's totally useless if all we have is an address space and no task. Because the task is the one thing that can track the progress of following the operations manual. In other words, if you just have an operations manual in a worksite and there are no boots, there are no bookmarks, and no one at the worksite, guess what? Nothing gets done, right? So that means if you are thinking about an address space, which is the operations manual in a briefcase, there's at least one task associated with each address space in order for address spaces to make sense. Is that okay?
Yes.
Okay. But you can have more than one task. Okay, so when you have one single address space, there can be multiple tasks associated with the same address space, but you need at least one task per address space for this to make sense. So now that we understand what a task is, we'll talk about something that is a little bit more complicated. It's called an enclave. Okay, this is IBM's term to refer to this concept here. It gets a little bit complicated, but I think we can just change our analogy a little bit to make it make sense. So in this particular case, we have a leveling job at a job site. Okay, so our job is to level the job site so that everything is flat and level. Now this time we require several operations manual. So the first operations manual may tell us how to level. The next one can tell us how to survey using the using a transit. Okay, if you look up the word transit as a tool, at a worksite, you will find what it is. It's basically something that can rotate on a tripod, so you can assess, okay, whether ground is level or not. If it's not level, you can also measure how tall, how much it is higher than the surrounding ground, and so on. So that's basically a level, and a surveyor is the person who would use a transit to kind of assess a work site and go like, okay, we need to remove 2 feet of dirt over here, and then fill that spot over there with 3 more feet of dirt, and so on. That might be another manual that tells us how to shovel. Okay, yes, I know shuffling is not a really complicated task, but we'll just say that there's another manual that explains how to shuffle. And then, shuffling doesn't do us any good unless you can move the dirt around. So there's another manual that will tell us how to transport dirt around. So now we have 4 manuals. Okay, in other words, we have 4 jobs that are normally stored on a DAS-D. Now, the main task that we want to perform is leveling. So that means we have one TCB created for that particular address space so that we can associate it with how to level. So we have one pair of boots and one bookmark created so that someone can can be in those boots and follow the instructions of how to level. So I didn't quite come up with the boots idea when I wrote this. So you can kind of imagine that TCB is basically what we just talked about, okay? A pair of boots to kind of keep track of where we are on the job site, and also a bookmark so that we can remember what was the last page, or I should say what is the next page of the operations manual to resume to when we get back to that task. So that's what a TCB is. Okay, so when we explained it earlier, we have already introduced the concept of a TCB.
Is a TCB a task control block?
Yes, a TCB is a task control block.
Okay.
And IBM really likes the term of control blocks. So there are all kinds of control blocks and also request blocks. SRBs is a service request block. I did not explain what a TCB is. I cannot believe it. Okay, so I'm gonna explain it here. This is a task control block. There we go. Okay. So now we have a subtask, okay? Because the manual that tells us how to level may basically create a whole bunch of subtasks, which is the first one is to do some surveying, okay? You're gonna use a transit, look around you, find out where we have excess dirt, where we have we have a cavity and we have to fill dirt into that cavity and so on. So the first thing is to survey. This is what I would call a subtask. It is not an IBM term. So if you look for IBM term subtask, you won't find it. So what we will do in this case is we're creating a subtask, and the subtask is represented by a service request block, SRB. And an SRB allows the instruction of a different address space to be executed. All right, so let's just pause here, okay? Because now we want to think about, okay, what do we mean by another address space? The active copy of the leveling operations manual is no longer sufficient, because what we want to do now is surveying. So now we need to refer to the active copy of the how to survey operations manual. But then how do we do this, right? So now we are creating a new bookmark. Okay, the new bookmark is called a SRB, and that bookmark is not a bookmark in the original manual, which is how to level. This new bookmark is now on the active copy of how to survey. So you can look at SRB as a bookmark that is on an operations manual of it's a different operations manual. It's in a different address space. So now the question is, but how can we use two different terms, right? Why is one called TCB and the other one is called an SRB? What is the difference? If they're both just bookmarks, then what is the difference? The difference is TCB, can contain some additional information. In fact, it can contain as much additional information as you would like. So, in the case of, leveling at a job site, if you want to track, how much time is used for the entire job, that information, okay, how much time is used for the entire job, that would be stored only with a TCB. So when you're performing the operations of how to survey, which is represented by the bookmark called SRB, the SRB itself doesn't track how much time is being used or how much time has been used for this entire job. It is the TCB's job to do it. So an SRB is more or less a component of a TCB when there is a subtask to perform. So is this analogy working okay or not? An SRB is a subcomponent of a TCB. When there's a subtask to perform, then we create an SRB so that we can keep track of the bookmark of a different operations manual?
I'm a little lost. I'm not gonna.
Okay, so first of all, there are two active copies of operations manual now. Because in the original operations manual, which is how to level, we get to the point where it says, okay, now you need to survey around you and find out, how much dirt we need to remove. But the manual that tells you how to level is not going to tell you how to survey, right? So now we need to move on to a different manual, and it is named How to Survey. So now that you have two different operations manual, you need two bookmarks, because you need one bookmark to remember where you were in all the steps of leveling, but you also need an additional bookmark so that you can keep track of all the things that you need to do when you're surveying. Is that part okay? That we need
So
two
the
bookmarks?
task would be how to level, and the task would be how to survey, and the service request block would keep track of where you are in each one of those tasks.
Almost. The original there's only one single TCB because there's only one task of leveling. So the TCB is still a bookmark of the manual that explains how to level. But when we need to open a new operations manual so that we can perform surveying, we now need to create a second bookmark. That second bookmark is the SRB. So
It's a service request block that you're requesting the service to complete the task.
Correct. So in this case, the service requested is surveying. So the service request block is here to keep track of the service requested, the progress of the service being requested. Is that okay?
I think so.
Okay. But all the accounting information, okay, okay, how much time did we spend? What about the expenses of this entire job? All of those stuff goes back to the original TCB. The SRB is a much simpler type of construct where it is just a single bookmark. It just needs to keep track of what is the next instruction we need to do in the subtask or the service requested, which in this case is how to survey. All right, is that part okay?
Yeah.
Okay. So this one seems okay. I mean, it doesn't seem too difficult. So we can basically just kind of move on to how to survey. And remember, there's only one person, except this person is now saying, okay, I am going to follow the service request block and finish how to survey first. And then it can go back to how to level to continue with the additional instructions of how to level. Go ahead. I thought I heard a question.
I think someone just cleared their throat.
Oh, okay. All right.
That's me, Jennifer.
Okay, not a problem. No worries. I just want to make sure that I, let people ask questions whenever they have questions. All right. So this time, we're gonna have something that's more important, more interesting. Okay. So what about when it's time to actually, shuffle and, basically, remove some dirt and then fill in, a cavity with some dirt? That gets interesting because now we have two subtasks that need to happen at the same time. Because shoveling is a subtask, and we know how to shovel from how to shovel as an operations manual. So that means we're going to create an SRB for shoveling because it is one of the subtasks. But it is useless if all you do is to shovel because you're just moving dirt from one local place to another place, which is really just next to where you're shoveling. All right, so that means you also need to move dirt. But when you want to move dirt, you need to refer to yet another operations manual that we call how to transport dirt. So now you have two SRBs created. one for each subtask. One subtask is shuffling, and the other subtask is transporting dirt. And the interesting part is, with these two subtasks, they both have to happen at the same time, concurrently, because it doesn't make sense that you just keep shoveling without moving the dirt around. And it also doesn't make sense to be just moving the dirt around, because you can just drive the little dump truck in the circle, it's not going to do anyone any good. So that means these two subtasks need to happen at the same time, and they need some kind of coordination. Okay, so we'll talk about coordination when probably in the next class or sometime next week when we talk about serialization. Okay, that's one of the kind of abstract concepts in operating systems, but we'll get to that part, and I think we can explain that. Okay. So this is when the concept of an enclave becomes important and also useful, because the whole concept of an enclave is it is a collection of TCB and SRBs. So we are now grouping at this particular moment, okay, at the moment where our original task, our main task is leveling, but it is time to shovel and it's time to transport dirt around. At that moment, we have one TCB and two SRBs associated with what we are doing. Those three things combined collectively is one single enclave. Is that okay? So we got basically three bookmarks combined as one single enclave. Now, why is this important? Because remember, no one is doing anything, because of TCB and an SRB, all they are just bookmarks, right? They are basically just bookmarks in an operations manual, so that we know what is the next instruction to follow in each one of the operations manual. But no one is doing anything. So now the question is, from the headquarters of this company's perspective, should we allocate a person to this job, okay, this particular work site? That has to do with prioritization, because if there's a more important job, we just leave this one alone. But on the other hand, if this one is the only job left, or it is an important job, and we have to get this done, then the importance is no longer associated with just the original TCB or just one of the two SRBs. The importance is now associated with all three. And that's why we have to combine the three things, which is one single TCB for leveling and two SRBs, one SRB for shuffling and one SRB for transporting dirt. Those three combined will now get the same importance level. They're considered basically, quote unquote, the same thing when it is time for the company to decide, well, should we assign somebody to continue with this job? Is it important to us? Now we consider all three as one single unit from the perspective of workload management. So is that concept okay? Why we have three different things, one TCB and two SRBs, what each one is representing, and why it is important to look at all three as one single enclave when it's time to prioritize. Should we assign a person to continue with this job? So I'm going to pause, I'm going to shut up so that you guys have some time to think about this and ask questions, if you do have questions.
Can you repeat that part? The three bookmarks that's combined into enclave leveling survey.
Sure, absolutely. Okay, so the TCB and the two SRBs are essentially, from a certain perspective, they're all kind of the same thing, because all they really are bookmarks to indicate in each operations manual what is the next step. So with only the TCB and the SRBs, nothing is getting done, okay? Nothing is getting done until the operating system dispatches the resources to to the TCB and the two SRBs, right? Because if no one is reading the operations manual and actually doing the digging and also the moving of the dirt, no work is being done. So the TCB and the two SRBs they're not work getting done. They are basically just telling us if somebody is to work on this job, what are the next steps to do? Is that part okay?
So the enclave is the two combined waiting for dispatch, basically?
Yes. So the enclave is basically the three things, because we have one TCB representing the original leveling job and one SRB to represent the subtask of shoveling, and another SRB to represent the subtask of transporting dirt. But those three, they belong to the same, basically, quote unquote, transaction. Using IBM's term, it's called a transaction. They're basically corresponding to one logical unit of work to be done. Is that okay?
Yeah.
Okay. So now the question is, since this construction company only has so many people to assign to all the different job sites, the question is, well, should we assign the person to continue with this job? So when the company does assign a person, when the company wants to decide what is the importance of this job, that importance is not only associated with the TCB, which is representing the leveling, but it is also associated with the two SRBs representing the current subtasks of shoveling and moving dirt around. And that's why the three blocks are now combined into one single logical concept called an enclave from the perspective of workload management. We can continue this on Wednesday because I think it's a little bit late. We have been talking about this stuff for a little more than 2 hours, and I know this stuff is kind of difficult to understand because they're very abstract. I have the super unfair advantage of being able to look at things from the inside out, because I don't write an entire operating system, but I do write simple what we call real-time kernels, but it is kind of like a miniature operating system. So these concepts are things that I have already implemented using my own code, so I can look at things from the perspective of inside out. But to explain it in a way that other people can understand is the challenge. So I do want to make sure that we have enough time for you guys to kind of absorb the concepts. So I think this is probably a good time to stop the lecture. But I do want you guys to spend some time to kind of think about these examples and all the concepts. And if you have questions, kind of jot down the questions and bring those questions back on Wednesday. So when we start the lecture on Wednesday, we'll start with this, okay? In fact, I'm going to put a TCB right here. This is what a TCB is. Where we left off on July 12th. That's basically what a TCB is, or SRB is. It is a way for a task to remember next time we come back here, where are we supposed to start? Is that okay? I mean, I'm trying to use the concept of TCB and SRB, just even when I just need to leave a little bookmark to myself, so that on Wednesday I know where to continue the lecture. That's basically what a TCB or SRB is about. Is where do we continue when we get back to this? Because now we have to move on to do something else. Is that helping?
So,
That makes sense.
Sorry? Yeah, go ahead.
Is this kind of related to like you put a job on hold, or that's different?
I'm not sure. Okay, when a job is on hold, it depends on what is the definition of on hold. So
Like
it depends.
suspended.
Suspended. So is the job halfway done or has not even started yet?
Well, well, actually, it's like batch processing where you program it to run a certain time,
Mm-hmm.
and then all of a sudden, one of the jobs related to it failed, so you have to put this next job on hold because otherwise everything will fail. I'm just curious if
Okay.
that's the bookmark where
Okay.
you
So from what you just described, the job has not even started yet because one job or the
right.
prerequisite job has failed. So the next job that relies on the result of the first job or the prior job cannot start. So it's not I think on a macro scale, it is the same thing because you're leaving behind a bookmark of going like, okay, we need to retry this job that have failed, then we might continue with the next job. So from that perspective, it is also a bookmark, but it is but a TCP and an SRP is a bookmark at a very, very, very low level because it's basically a bookmark of what is the next location in the address space is the next instruction that we need to execute. So it's a question of um, how low of a level we are talking about. Jobs are at a very high or macro level, and then what we are talking about here is pretty much as low of a level as we can get because in software, the granularity of talking about how much work can be done, the smallest grain of how much work can be done is a single instruction um, in an address space. So from that perspective, we are looking what we are talking about here as a TCP or SRB is at the pretty much lowest possible level where we can leave a bookmark.
Okay.
Okay. All right. So I think you guys probably need some time to kind of let this stuff sink in. And as you think about this, if you have any questions, go ahead and write down the questions. Or you can also ask your questions using the channel chat because the video chat is going to go away as soon as we terminate the meeting. But the channel chat is persistent. So if you want to ask questions using the channel chat, I will get to those questions as soon as I can. And my communication policy in the syllabus also specifies that I will get to that within 24 hours. So that would be a good resource to use as well, is to kind of ask me questions, before the next class. And if you do it on the channel chat, then everybody can see it too. So that will help the entire class. All right.
Got
Okay.
it.
Thank you.
You're
Thank you.
welcome. Thank you.
Thank you.
Good night.
Yep.
See
Good
you
night.
Wednesday.
Yep. Rest well.
You too.
All right. Thanks.
Bye.
All right. Bye.